This is E658, lecture 16. So in the last class, we were talking about fully differential operational amplifiers, and the first step to making a fully differential operational amplifier was this guy here. And as we discussed yesterday, in order to get a large incremental gain, what you want to do is to use current sources as loads. So the incremental gain you get will be GM times output impedance of the NMOS transistor parallel the output impedance of the current source. So the first step to make sure that this in fact works as intended is to set the differential input to 0, which means that this input will be VCM I. This will also be equal to VCM I. Please note that the operational amplifier is intended to take two inputs, one of which is VCM I plus VD and another input which is VCM I minus VD, and produce VCMO plus some large gain times VD and VCMO minus a large gain times. This is the intention, and this is quite analogous to a single-ended op-amp, where the only difference being that instead of referring the output to ground, the output of interest is the difference between these two nodes. One thing that we need to make sure from this block diagram is that if you set VD equal to 0, what should the two outputs be? They should be sitting at some constant voltage, VCMO, which represents the common mode output voltage of the differential op-amp. Can you comment on what VCMO should be in order for the transistors inside the op-amp to be operating in their active regions? Please note that in this diagram here, this is one output, this is the other output. I mean, this is the simplest case of an op-amp that you can think of. You can do other things to increase gain and reduce output impedance and all this other stuff, but for a start, this is good enough. So if both the inputs are held at VCMI, in other words, the differential input is 0, both the output nodes must be sitting as per this block diagram at VCMO. So if both must be sitting at VCMO, can you comment on what VCMO should be in order that the transistors M1 and M2 here operate in their active regions? Clearly, you want VCMO to be at least as large as VCMI minus VT. In practice, you would want VCMO to be much larger than VCMI, because it's not, you're not going to keep the op-amp like this. The op-amp outputs are going to be swinging, and you want to make sure that even when the signal is swinging, the transistors do not get into the triode region. Now, let's see if that is possible. Okay, so this circuit is, one thing that becomes immediately obvious when you look at this circuit is what? The first obvious thing is symmetry. So you can at least simplify analysis by, so whatever happens to the left node also happens to the right node. So it is just sufficient. So one thing I could do to reduce transistor count and therefore ease up my life is to short the two, right, as far as analysis of common mode inputs is concerned. Now, can you comment on what this voltage will be? What I have done so far is a perfectly legal thing to do. I have taken two transistors, identical transistors M1 and M2, joined their sources up together, put a tail current source of 2I, joined their drains together, as in this diagram, and have a single source. This is equivalent to a single source of current, 2I, being pushed from the top. Okay. So can you comment on what this voltage will be? You have two current sources. What is the drain current in M1? Without knowing anything, you can say it must be I, because by symmetry the current 2I must flow equally in both transistors, regardless of the region of operation. The way you have it here, the current will be I. So equivalently, if I look like this, it's like having a current source of value 2I, and I am pushing from the top another current source of value 2I, and what I am interested in is the potential VCMO. So what is, two current sources are fighting, obviously Kirchhoff's law at that node is satisfied. So what is the potential at that node? It can be anything. I mean, it could be greater than VCMI minus VT, it could be smaller. So whenever two equal current sources are fighting against each other, the potential of that node is indeterminate, because by definition a current source is something which will keep supplying that the current it is supposed to, regardless of the terminal voltage across the current source. So as such, we cannot at this point figure out what VCMO will be. That is only part of the difficulty. In practice, what did we say? We said that these are independent, I mean these are all current sources. So what do you think will happen to this potential if this current, this 2I, you know that in practice it's impossible to get two current sources to be exactly the same thing, right? They will be always, if you make two nominally identical currents, you can be sure that in practice the two may not be exactly identical. So the current pushing is 2I plus delta rather than 2I exactly. What can you say about this node potential? It will go on increasing, because the net current is flowing into that node, the node will keep floating up. Eventually, in principle, in this diagram it should go to infinity. In practice, you know that those are all current sources made with transistors. So the moment the voltage goes higher and higher, the current sources no longer behave like current sources, and the devices will get into the triode region. By the same token, if the pull down current source was larger, what do you think will happen to VCMO? Eventually go to some low value like ground. The problem is happening because the pull down current sources and the pull up current sources are independent of each other, right? Because these are independent current sources, the potential at this node cannot be set at all, because even if they were exactly identical, first of all, there is no, you cannot set this potential to be, I mean, this potential is unknown, okay, but maybe you get lucky and somehow it happens to be the range that you want, alright, but in practice, these two will not be exactly the same, which means that in all probability, the potential VCMO will either be ground, close to ground, or close to VDD. So the problem is that these are independent current sources, and another corollary from this whole discussion is the following, that is, let's say you had two current sources and you wanted to figure out which one of them is larger. So what would you do? One way of doing it is to hook them up like this, correct, and compare this potential to some constant. If this potential keeps rising, it means that the pull up current is larger than the pull down current. This is called the pull up current because it's pulling the potential of the node up. This current is called the pull down current because it's pulling the node potential down. So one convenient way of figuring out when if one current is larger than the other is to simply make them fight in this manner and compare the node potential to Vref. If the potential of this node keeps increasing, you know that the pull up current is too high, okay. If it is, if this node is falling down, you know that the pull up current is too low. You know that the only way in which this potential can remain constant is when, see, when these two currents are exactly the same, the node potential will be constant. You don't know what that constant is, but it will be a constant. So if you want to make a current source which is exactly, if you want to make this current source exactly equal to this current source, what you need is a tunable current source, and this is what you would pretty much do in the lab, right? You make this current source fight against the pull down current source, keep monitoring the potential of that node and go on tweaking the control knob on the top current source such that the potential at the junction stays a constant. So, coming back to our situation here, we see that if this set of current sources is completely independent of 2I in the tail, then the output common mode voltage cannot be established at all. In all probability, it will either be too high, which will cause these current sources to go into triode, thereby reducing gain, okay, or this potential will go so low that M1 and M2 will get into the triode region, again reducing gain to incremental gain to a very small value. So that is the problem. So what is the solution? I mean, the problem was that this set and this set are, this 2I and this 2I are independent. If they were made dependent on each other, then you'd be able to make that voltage stay at a constant potential without going either to ground or to VCC. So, if you want to make, I mean, you have two current sources. There are many ways of making, I mean, for example, you could make this chap dependent on this, or vice versa. I'll take a simple example where I'll make the top current sources depend on the bottom one. So, if I want a dependent current source, I must be able to, I want to change the top current source to make it equal to the bottom current source. So, first of all, I must have a current which is capable of being changed. Okay. So, what is the simplest device structure you know which will allow you to vary the current, that will allow you to push current and you will be able to control the current using a knob? What kind of transistor? A PMOS transistor. This is VDD and this is the control knob. If this knob goes too low, what happens? The pull-up current becomes very high. If the node potential here goes too high, then the current being pushed will become too small. Okay? And you want to make this current, the sum of these two currents exactly equal to 2I, so that the output common mode voltage will be maintained at some value that you want. So what will you do? Very good. So the basic idea is the following. You want to measure, you want to have a box which somehow measures the common mode okay, and if you have two nodes, what is the common mode voltage? What is the definition of common mode voltage? It's simply the average of the two. So there are any number of ways of finding the average. One simple way is to simply put two resistors, equal resistors, and the midpoint of the two of them will give you the average value. So you measure the common mode voltage and you compare it with a reference which I will make equal to VCMO, my desired common mode output voltage. So if this voltage is too high, what does it mean? If this voltage is high and is going up, it basically means that the current pushing into this node, the common mode current into that node is too high and it has to be reduced. So, if the current is too high, what will you do to reduce the current? I must increase the potential at the gate. In other words, if this goes up, this must also go up. So what are the signs of the op-amp? Plus and minus. And thanks to this negative feedback loop, now these two current sources are dependent on this tail current 2I, and the negative feedback loop ensures that this potential, which is the common mode voltage at the output of the op-amp, is exactly equal to some desired reference that you set. And you should set the common mode voltage such that the transistors M1 and M2 will operate in the saturation. Please note that this loop only operates on common mode signals. So if, for example, you now apply a differential mode voltage input, so if this goes up and this goes down, what do you think will happen to this node? This will go down and this will go up by equivalent opposite amounts as long as the currents are, the input differential voltage is small. If this goes up and this goes down by equal and opposite amounts, what comment can you make about the common mode voltage at the output? There is no change at all. So if there is no change in the output common mode, this voltage doesn't change, which means that as far as the op-amp is concerned, which is kicking this node, nothing has changed for it. So this loop, which operates only for common mode signals, is called the common mode feedback loop. The job of this loop is to hold the output common mode constant. The last thing that I need to discuss is how will I measure the common mode. Okay, one simple idea is to use, as I said, the output common mode is simply the average of the two output voltages. So if this was VIP, VIM, VOP and VOM, to find the average, a simple thing to do is put two resistors like this, and this should give me VCM. This is one simple cheap way of measuring the output common mode and going and tweaking the top current sources such that they exactly equal the tail current. So what is the problem with using two resistors? The adding two resistors to find the average of the output is a perfectly normal thing to do as far as the common mode loop is concerned, right? But we should make sure that in our whole endeavor to try and measure the output common mode, we shouldn't screw up the differential mode. After all, we are trying to realize an amplifier with a large differential gain. So what is the differential gain now? Differential mode gain? Assume all the transistors have infinite output impedance. It's simply Gm times R. So for differential signals, what happens? This goes up, this goes down. Similarly, this goes down and this goes up. So for differential signals, this doesn't change at all. So it's the midpoint is like ground. If this is going up, this is going down, the middle node doesn't change. So what is the incremental gain? It is simply Gm times R. So the problem with this, so this is one example of a, what is called a common mode detector. Okay. So the problem with the resistive common mode detector is that it reduces differential gain. So can you suggest something which will sense common mode but does not reduce, will still not reduce differential gain? The problem is that when incremental current flows like this, it's all flowing through the resistor. Okay? Ideally, you want all that current to flow into an open circuit so that you get as large a voltage gain as possible. So you want to be able to sense this voltage, but you don't want current to flow. So what is the logical thing to do? If you put a voltage controlled voltage source, So this is VOM, this is VOP, this is R, this is R. So now you have a common mode detector where the output is proportional to the common mode, but the common mode detector does not load the differential mode signal paths in any way. So when you have differential mode signals, you will all, it makes sense. It's an obvious consequence is now you could have different impedances for both differential mode signals as well as common mode signals, right? So for example, to give you so if I had two resistors like this, and this is VA and VB, when operated differentially, what is the impedance? If I push this up by V and pull this down by V, what is the ratio of voltage applied to current flowing? What is it? If this goes up by V, this goes down by V, so what is the current flowing? V by R. And what is the voltage applied? Differential voltage applied is 2V. So differential mode input impedance is what about the common mode impedance? When both move up by the same amount, how much current flows in? The idea behind this discussion is just to motivate the fact that when you have a network, you can have different impedances for differential mode signals and common mode signals. So what is if VA and VB were excited in a common mode fashion, in other words, if both of them moved up by the same amount, what would be the current flowing in? 0. So what is the common mode input impedance? This is infinity. Okay. So you have this box. Okay. You don't know what there is inside the box. You have two terminals, A and B. So if you want to find the common mode impedance, what will you do? I will short these two terminals together. Alright. Apply a delta V. Measure the delta I. And delta V by delta I is my common mode input impedance. On the other hand, if I want to measure the differential mode input impedance, what I will do is to connect delta V by 2 minus delta V by 2, okay, and measure the current that flows in and do the V by R. So, alright, so let me ask you another question. So what is the differential mode impedance? What is the differential mode impedance between A and B? The same thing as before. Alright, so what is the common mode impedance? R by 2. Now, what is the differential mode impedance? To R. What is the common mode impedance? It's 2.5R, right? So the impedance offered to differential mode signals can be very different from the impedance offered to common mode signals. Okay, so now that you understand that there is nothing fundamentally wrong with the idea that the impedances can be grossly different for differential as well as common mode signals, let's now try and evaluate the differential mode and common mode input and output impedances of our elementary op-amp that we have just designed. Let's assume that we have an ideal common mode detector which doesn't load the op amp, an ideal amplifier who kicks this the gate of the PMOS transistor so that they behave. Alright, and this is VI, P, VIM. What is the input impedance? Differential. Let's do only DC values, okay, low frequency input impedance. What is the differential input impedance? What is the differential input impedance? Infinity. Why? Gate is an open circuit. Yeah, okay. So differential input impedance is infinity. What about the common mode? It's easy, infinity. Okay. Now, what about the output impedance? You assume all the transistors have infinite output impedances. So what is the differential mode output impedance? What will I do to find the differential mode impedance? Apply a fully differential excitation at the output and measure the current flowing. Correct? So if I apply a voltage source such that this goes up and this comes down by exactly the same amount, what happens to this node? That node remains the same. Okay? If that node remains the same, what can you say about this node? That node doesn't change either, because that's simply an amplified version of this node voltage. So in other words, if I apply a fully differential voltage excitation at the output, this node doesn't change. So incrementally it is equivalent to grounding it. Okay? So in the small signal picture for differential operation, you can ground the gate. So what is the output impedance of looking in differentially? It would be this guy, the output impedance of this transistor parallel the output impedance of this transistor. Also because if the input, if I purely apply differential excitations to the output, this node potential will also be, by symmetry, this node potential must not swing at all. If the transistors were ideal in the sense that they had infinite output impedances, what would be the differential mode output impedance? It would be infinity. What about the common mode output impedance? What will I do to find the common mode output impedance? For common mode output impedance, what I would do would be to short these two guys and apply a small signal, say current, and measure the change in voltage. So if I pump in a current like this, what do you think will happen to this node potential? Assume that this is an ideal op amp. It will stay at VCMO. Why? What do you think will happen initially? If I try to pump in any current into that node, the potential will tend to rise. Okay? And as soon as the potential rises, it will get picked up by the common mode detector. Right? The moment the common mode detector output goes up, the op amp now knows that there is some mischief going on. Right? So it knows that the output common mode voltage is too high. That means the current being pushed into the node is too much. So it does all that it can to bring the potential at the left node as close as possible to the potential at the right. That's the job of the op amp. So the moment this node potential tends to go up, the op amp will go and kick the gate of the PMOS transistors here so hard that the potential comes back to. So if the op amp is ideal in the sense that it's infinitely fast, this will happen without you even knowing it. In practice, of course, it will take for some time for the op amp to react. So what do you think physically, if you put a real op amp without knowing anything about the details, what kind of voltage would you expect at the output? If I put a pulse current like this, initially what will happen? Initially the potential will rise. During that point, up to that time, the op-amp is virtually sleeping. Okay, it wakes up and then suddenly goes and kicks the gate. Then what happens? So this is the kind of jump you can expect to see in practice. If the op-amp is slow, what can you expect about this peak? So this peak is proportional to how long the op-amp takes to wake up. So if this op-amp here is very fast, then even for a small, the op-amp wakes up very quick, so it will just do that. If the op-amp is too slow, right? This is the step current you pushed in. If the op-amp is very slow, what happens? This will tend to do this, and then the op-amp realizes something is fishy and then goes and does the right thing. On the other hand, if the op-amp is fast, probably does something like this. Eventually they will all come back to 0, because if the gain of the op-amp is sufficiently large, then in steady state there will be no error. So if the op-amp is ideal, what can you say about the output impedance? 0, because by injecting an incremental current into the output node in the common mode fashion, the output common mode voltage has not changed. It is in fact 0. The output voltage is the incremental change in the output voltage is 0. So the incremental common mode impedance is 0. So you can see, not surprisingly, perhaps, that reiterates the fact that it is possible to have very, very different impedances for both common mode and differential mode signal. Here you can see the situation where the differential mode impedance is infinite. So for differential signals, it's an open circuit, but for common mode signals, it's a short circuit. So as far as the differential mode equivalent circuit is concerned, one thing you notice with this op-amp is that the differential mode equivalent I will draw only the half circuit. Okay, this is the small signal equivalent half circuit. The gate of the PMOS transistor is grounded, because for differential signals that this common node doesn't move. This is the positive half of the input voltage, and as you can see, the incremental gain will be minus GM times RON parallel ROP. So one thing that I wish to point out is that the output voltage gain can be very large, but the output impedance of this this is basically, for differential mode signals, is behaving like a voltage controlled current source. So this is VIP and this is VIM. The reason I went to this whole discussion is to motivate the model for the op-amp used in your assignment 2. In this example, this is one example of how you can model a fully differential operational amplifier. Okay, this is not exactly equivalent to, this model will not fit the stuff that we derived here, okay, because what we have here is for differential signals, what we have is a voltage controlled current source, whereas what we show here is a voltage controlled voltage source, okay. But in both cases, the common mode output impedance is, what is the output impedance for common mode signals here? This is your op-amp. This is VOP, this is VOM. So what is the common mode output impedance? 0. And what is the common mode output level? I mean, by construction, the output common mode is VCMO. And so the input common mode, what is the input impedance for both common mode and differential mode signals is infinite. And it turns out that it is quite straightforward to convert this character into something which has very low output impedance even for differential mode signals. Can somebody suggest a cheap way of doing it? I mean, one thing I could argue right away is that if I treated, since anyway I already have voltage controlled voltage sources, if I imagine that these were the outputs of my, within quotes, amplifier, right? Then the differential output impedance at these two nodes is 0. The common mode output impedance at these two nodes is also 0. Okay? And in practice, this X1, which are buffers, can be implemented by using a common drain. So, all of you realize that this represents a differential voltage controlled voltage source, whereas this represents a differential voltage controlled current source. In both cases, however, the common mode output impedance is 0. And one easy way of converting this differential, this has got a large DC gain. However, the only problem is that the output impedance is very large. I mean, you can think of a voltage controlled current source as a voltage controlled voltage source with a very, very large output impedance. Okay, this just follows from Norton Thevenin. So, one way of retaining the large voltage gain but getting rid of the high output impedance is to simply use a voltage controlled voltage source at the output of this chap here, correct? So this way you have both, you have high gain as well as low output impedance. And if I treated these two as my outputs of my op-amp, then it will conform to this model. And this is the macro model I've given you as the model to use for your assignments. Because I don't think we'll have time to get into the details of the op-amp in this class. Okay. So we'll have to make do with macro models. And to model the finite speed of the op-amp, what we do is not have this controlled by VIP minus VIM, but a low pass filtered version of VIP minus VIM. And one more thing that I wish to point out with regard to your assignments is that if you use this ideal model, if the gain is large, then if during transients sometimes the difference between VIP and VIM can become say 25 millivolts, okay, or something even larger than that. If you put 25 millivolts and this is a voltage controlled voltage source with a gain of 1000, then you will get 25 volts, and that is clearly outside the range over which this op-amp is sitting in with switches and capacitors and all this stuff. The switches are all MOS transistors. Those models are only valid when the supply voltage ranges from 0 to 1.8 volts or 2 volts or something. The moment you exceed these supplies, okay, the models will go crazy and the simulator will complain like mad. Okay, so what you have to do is to limit these voltages to 2 volts. Okay, so I believe Eldo has got a feature to do that. Okay, so that's something that you want to use. If you're using cadence, then just put a Verilog A voltage clamp, which makes sure that the moment this voltage attempts to rise above 1.8 or 2 volts, it will just clamp at 1.8 volts. Okay, all right, stop.